as I go through, ask any questions as I go through while the slide's on the board rather than having to go back. So this is just a talk really to give a setting, to give a feel for the place. It's not meant to be, specific, just I think something they should do at schools to make people aware that, hey, the Earth is really quite extraordinary. And I just hope this works. Oh, it did, yeah. So I've put in the known universe, there's up to about 10 to the 24, that's 10 with 24 zeros after it, stars. And no star has been found yet without a planet, that they can say there's no planet around that star. So however many stars there are, there's probably 8 times as many planets. And in the Milky Way, there's itself just one galaxy, there's about 200 billion. And this is the configuration of the planets around Earth, around the Sun. And that just shows how insignificant Earth is. Among all those planets, it's a tiny little spot. And this is an idea of time, that it was not until the Phanerozoic that we had macroscopic life that you could see without a microscope. And planet Earth is really quite extraordinary. It's just about the right distance from the sun, not too hot, not too cold, the Goldilocks zone. It's got enough gravity to hold an atmosphere and water at the surface. Is that sun in your eye?
I think it'll pass though. Give it a few minutes.
Yeah? Yeah. Yeah, that happens, doesn't it? I was just talking about that. And the atmosphere changed from this, a lot of greenhouse gases, a lot of carbon dioxide, no oxygen, to this, quite different. And it's got a magnetosphere, a magnetic field around it that saves us from solar storms, getting zapped.
Can I ask a question? Sorry to be a pest. On my last slide, why did the atmosphere change?
Well, we'll touch on that, but not completely. But photosynthesis was the big changer. That was we talk about photosynthesis in permaculture and how important it is, but from the history of our atmosphere, photosynthesis has been critical. And it's a very active planet. There's 500 earthquakes a year over magnitude 5, and that's, they're quite significant earthquakes. And accompany those is often volcanic activity, so a lot of new materials being brought up to the surface all the time. We talk about new minerals being brought to the surface, they're nutrients that have been brought to the surface, nutrients for people who do permaculture. About 45 million years after it was formed, it was hit by a very large celestial object, and that tilted it on its axis, and that gave us, that then formed this big splash, formed the moon. That gave us our tides and our seasons, and it would be hard to imagine Earth without any seasons and without any tides. And this is the story of photosynthesis. The oldest fossils we have, and they aren't actually fossils of animals, they're fossils of the structure that was left behind, not that they built, but they formed a very sticky surface to which calcium carbonate stuck to and grain stuck to. And they form these features called stromatolites, but they're the first evidence we have of beings that photosynthesize, because we have these we have very similar ones today in actually about the same area. This is up in the Pilbara, and next door we have them live. And this is the chemical reaction of photosynthesis. So it forms glucose for them to build, and oxygen. And this is where you can see them in Shark Bay. And we have some down the coast here, some tiny little ones. And the other aspect of forming oxygen was then converted in the stratosphere to ozone, and that protects us from ultraviolet light. That enabled life to migrate onto dry land. So this just gives an indication of when first life occurred, and that's very questionable. Even questionable about what is life. When does a molecule become life? It's actually when it reproduces, and we really can't work that out. And photosynthesis probably occurred then, but it may have been earlier. And all of the oxygen initially went into the ocean, and then the atmosphere began oxygenation, but it wasn't until just before the Phanerozoic, in fact, that macroscopic life appeared on Earth. And it has enough greenhouse gases to keep us comfortable, and we hope that continues. And because it's got such a mobile lithosphere, I don't use the word crust, it's the lithosphere, and I'll come to that. And a lot of it's been broken up and separated into various continents, islands, that it's been able to have an environment, a range of environments for evolution of various life forms. And this is how we envisage ancient Earth, and yet if you go up to the Pilbara, this is what you'll see. 2.7 billion years old and more, and sediments there that are absolutely deadly horizontal. They weren't disturbed by tectonic activity or by storms when they were laid down. They haven't been disturbed since. And yet today we have this. It is such a different story to, and I hope I don't offend anyone, to the biblical story of the earth was created for us, and here it is all safe and sound. We're still about halfway through the story of Earth, and it's still very active. You can see it's basically a molten planet. It's just got a very thin lithosphere, which is the solid part. And this shows the aspects of the lithosphere. There's the crust and the solid part of the underlying mantle. And it's been moved around by these convection currents, which are there due to the latent heat of the formation of the planet, and also atomic breakdown of elements. And probably the best known.
What's that lithosphere? Is it you applying wood mill, or like you got the crust, and then is it like the crust is?
Yeah. Okay. The crust is probably best explained in the continental crust, where you've got the lighter rocks, granite, floating to the surface after 4.6 billion years. The lighter material floated to the surface, and beneath that is the mantle, and the mantle goes down well beyond what I've shown here, but at this point called the moho, the mantle is solid there, and then I don't like using the term liquid, but it's plastic underneath, it's molten. Yeah. And these act as one part of a tectonic plate that moves around. And these are collision areas, and we'll have a look at some of these. And remarkably, in Western Australia, we have aspects of every one. And we'll have a look at that. And this is probably the best known, is how the Americas drifted westward away from Europe and Africa. And you can see it in the formation of the Americas, where you've got the Rocky Mountains all down the leading edge on the western side and the Andes down here. And the trailing edge, if you have a look at Google Earth and look at that trailing edge and just look at the elevations, it's 1, 2, 3 meters above sea level right down the eastern coast of America, because that's just been dragged along as it moves to the west. And this is where you can walk down there with America on one side, Europe on the other side. Just an aside to this big trench down the middle, this big crack down the middle, was found when the Russians had nuclear submarines and the Americans wanted to find out whether the nuclear submarines had, so they sent out ships with sonic to search for them, and they recorded the data, but there were no women on the ships. They sent all the material back to what they call I think they call the computers. Anyway, to the women in the office. And one of the women, Marie Celeste, can't think of her name, she said there's a big crack right down the middle of the Atlantic Ocean. And she was called a silly girl. And eventually she convinced her boss that this happened, and they wrote a paper. It took about 3 years for her message to get through, and they jointly wrote a paper, and he took most of the credit for it. You'd hope times.
Is it the Mariana Trench? Is that what you're saying? No, that's not the right side.
No, the Mariana Trench is, yep, no. No, this is the, this is the Mid-Atlantic Ridge. And it's a ridge because as it parts, you get a lot of volcanic activity, and it lifts up and there's a ridge. Yeah. And you can walk down it. This is in Iceland. And Iceland, of course, is still very active. There's volcanic activity right now. And this is when the Atlantic Ocean began to form, geologically sort of yesterday. And just one other major tectonic event of India colliding with Eurasia and pushing up the Himalayas, that being Mount Everest. And again, that happened fairly recently. Okay, so that's a very broad story of Earth, and we'll look at now at Western Australia. Western Australia is made up of, there's 3 major types of tectonic plates or tectonic elements. There's the cratons, which are old and almost inactive, but they're not, no area is inactive, but they're old and stable. And Western Australia has 2 and arguably 3 cratons. There's the Yilgarn craton, and the Pilbara area, and also the Kimberley Basin, which is a very old basin, goes back to the oldest part being about 1.1 billion years, and it's been stable ever since. So that could be called a craton. The origins are collision zones of cratons of which some have moved away since then. And the basins are obviously the sedimentary basins where sediments have been eroded from cratons and other areas and dumped into large troughs. You can see the ages here, they're very old, like the Pilbara goes back to 3.6 billion years, and even the collision zones are all over 1 billion years old, apart from some up here which are a little bit younger. So it's very old and very varied. There's sediments, there's metamorphic rocks, and if we look at the Yilgarn craton, that's the ages for the craton, and it was formed by an accumulation of tectonic plates. So there's stable areas, there's collision zones, and there's a whole range, and therefore a whole extraordinary range of minerals there. And this is when the Yilgarn was formed. And the last volcanic activity, the last time fresh minerals were brought up onto the Yilgarn, and this is only on part of the Yilgarn, was over 1 billion years ago. So it's seriously old. And this area down here where we sit is an area that's quite a bit younger. Started forming about 1.1 and to 500 million years old. So it's quite different to the Yilgarn, which is around this age. And it was formed during the formation of Gondwana, where India, and here I've called it Greater India because it was bigger then, and as we'll see, some of it slipped under Eurasia to push up the Himalayas, and Antarctica collided. And these are the collision zones. There's the Albany-Fraser origin, where Antarctica collided with Australia, and the Pinjarra origin, where India collided with Australia. And as India collided with Australia, there was metamorphism. The minerals were changed, and as they changed, they aligned themselves normal to the pressure. You can imagine the easiest way for a mineral to grow is not into the pressure, but normal to it. And you can see that quite clearly in Cape Naturalis and all the way down to Cape Leeuwin, where the lineation is very definitely north-south. And oddly enough, the only geology reports I've seen in this area, and I've looked at a lot of them, are from geologists walking up and down the coast. If we go to the boat harbour in Augusta, you'll see quite a different formation. It's horizontal, there's no lineation, and this is an orthosite, and an orthosite is considered to be the result of a big magma chamber settling through gravity, and this lighter material comes to the top. And this is where I've noticed an orthosite. Most of our farmers are an orthosite. So it's not the simple story of India smashing into Australia. It's more complicated than that. And there's a lot of questions yet, which makes it interesting, I guess. And then about 500 million years ago, India started moving off. And it formed a trough in which sediments were deposited. This is the beginning of the Perth Basin. And the first part was up in Kalbarri. And this is the attraction here, but if you just walk about 5 or 6 metres down the track, you'll see these little footprints. And this is where some of the first animals began moving onto dry land. These little arthropods called eurypterids. And you can imagine a tidal area. They would be in seaweed. They'd be progressively been getting used to living in a non-marine environment and then a dry environment. And then by 300 million years ago, that India had moved away enough that there's a big trough open between about Rosabrook and Nannup, and that's the Bunbury Trough, which is an southern extension of the Perth Basin. And this was during the Permian period, where it probably looked something like that. And the interesting thing is, it looked like that, and there was a relative absence of animals. So there was a lot of photosynthesizing going on. So a lot of oxygen produced, and when a lot of oxygen is produced, those that depend on oxygen generally grow bigger. And some of the insects back then were of this size compared to what they are today. Oxygen levels were over 30%. Today they're about 20. This is when coal deposits were laid down, mainly in the Bunbury Trough and further north in the Perth Basin, but elsewhere throughout across the world. And all that oxygen, all that carbon taken out of the atmosphere reduced the greenhouse gases. This is just a time scale to show where we're at. Reduced the greenhouse gases, and the world went through a very cold phase at the end of the Permian. And that's the coal that we are now burning to reverse the process. So a lot of Western Australia was glaciated, and it was glaciated not because of the global temperatures being colder, it was further to the south at this time. And when it's glaciated, it scrapes the surface clean, it exposes new minerals, but this happened about 280 million years ago. It was probably not all glaciated, a lot of it was. So most of Western Australia is at least 280 million years old in the sense that it's been exposed to the atmosphere, to weathering for that time. And since then, relatively mountainous terrain has been weathered and basically eroded, and the sediments dumped into adjacent troughs or offshore. So in broad terms, this is where you get the minerals where they've been exposed, and this is where you get the oil and gas where the sediments have been dumped. At the end of the Permian, there was extraordinary volcanic activity in Siberia, and this is what remains of some of the lava flows there. They were really very extensive. And greenhouse gases, firstly there was shading of the atmosphere. It went through a very, very cold stage, and then greenhouse gases came into effect as warming and a mass extinction. Probably 95% of all species were extinguished.
So, Peter, you said the greenhouse gases came and caused this extinction. Where did that come from? Where did the greenhouse gases come from?
From the volcanic activity, yeah, and it was more than just from the volcanoes. It ignited coal seams, and it probably went through salt deposits as well, and there's a lot of chemicals in those that added to the extinction, not the greenhouse effect, but to the extinction. Yeah, it was probably quite a poisonous time.
The lack of plants then at that time as well, like you said, the plants had all started to get frozen over.
Sorry, the lack of plants.
Yeah.
Is
that at the same time?
Yeah, no, the plant growth was pretty good during the Permian. And when they talk of mass extinctions of, say, 90% of species being extinguished, they talk about species, but they don't talk about numbers. And probably a lot of plants survived during that time. So the number of, the amount of vegetation was reduced, but nothing like 90%. And the big losses were in the ocean, and particularly in the equatorial regions where there's just a huge number of species, and yeah. So the south of WA at Bremer Bay, there's a seismic line shot, which I had a look at, and this is where Antarctica was up until about 1.1 billion years ago. And this is the seismic line. You don't have to be a geophysicist to see that this is an indication of sediments. Here it's granite where there's just no reflection. It's a complicated situation. And you've heard of the big canyons off Bremer Bay, and they're deep enough that they could identify enough sediments to say that this commenced about 160 million years ago, that sedimentation, which means Antarctica started moving away from Australia, from Western Australia at that time, which is a lot earlier than had previously been thought. So this was the first aspect of southwest of WA being isolated. And this is the type of sediments that then prevailed in the Bunbury Trough. And this is when the first marsupials evolved. They evolved not here, but in America. Although the Chinese think they evolved in China. $130 million years ago or so, India actually broke away from WA and left a little bit behind, and that's the bit we're on now. And you can see where it had collided and then broken away from is the Darling Fault. And that fault can be traced positively almost to the Shark Bay area, but also tentatively up to Onslow.
So that part is all Little India?
Sorry?
That part is all part of India.
No, this is now full of sediments, almost full. But this was India here, and it's drifted off, of course, yeah. And at the time it left, there was a lot of volcanic activity up through the Darling Fault, where India had parted, and that basalt just filled the valleys, and this is been identified by aeromagnetic data, and you can see it's quite extensive. If you go to Bunbury, that's where it's easiest to see this basalt. I think we might skip that, but it didn't just leave the Leuven complex. There's another basin here and another plateau out further to the west. And this is the whole Perth Basin area. After it left, this sort of sedimentation continued, and that was the environment, something like that. And I've just shown this because this is the Leaderville Formation, and the preceding formation was the Yarragadee Formation, and they're the main aquifers here. That's where the water comes from for Margaret River, for Busselton, and they even take it from the Nannup area for towns further to the east. So it's the most important system, both the Yarragadee, the older one, and the Leaderville Formation. And just to give an idea of what an aquifer is, you can see it in this photograph of a beach sand and a creek running, and it goes straight through the sand because the sand's got porosity and permeability. And these sands that are deposited in that situation have those characteristics, and even through the geological process of being buried and compressed, they retain porosities maybe ranging from 10 to 25% porosity. So 25% of it will be holes and connected to give it good permeability. So for the next 114 million years or so, there's no sedimentation in that region. And you can see that before India had moved away, that these are the sedimentary basins in the south. And after India and Antarctica had moved away, you can see how they've retreated to the north. And that's because of the weight of Antarctica and India being lifted, and the lithosphere, the crust, simply rose up. So as it rose up, we had the formation of the Blackwood Plateau. This is a real plateau, and the Blackwood Plateau is like that. If you've driven from here to Nannup, you'll know it's not a plateau at all. And the reason for that is that it was lifted up very early after its formation. After the formation of those sediments, they weren't compressed, they weren't very solid, they were very easy to erode, and that's what they did. They eroded, and a lot of gullies. So there's no deposition all the time from the extinction of the dinosaurs right up to the present. And yeah, I just mentioned that 52 million years ago is the first fossil of a eucalypt that's been found. That was in Patagonia. And at that time, southern part of America, that's South America, and Antarctica and Australia were joined. And marsupials then migrated to Australia.
Oh, so they definitely rose up in the Americas and South Americas, marsupials.
Well, in North America, and then migrated to South America, and then to Australia. And there's only one species left in North America. And I think we have about 160 species here, yeah? And what I consider to be iconically Australian, or also the monitors migrated from Indonesia down to Australia about that time, yeah. And then as these continents moved apart, the formation of the currents changed completely, the ocean currents changed completely. That was the formation of the circumpolar current, and that is the strongest current in the world, and it has a profound effect on our climate. So climate changed dramatically at that time. There was some continental ice formation before that, but this is really when Antarctica froze over. And just to give an idea of the importance of ocean currents, and in this case the Antarctic circumpolar current, look at these cities, Santiago, Cape Town, and we'll call Margaret River a city, all at the same latitude, and yet we have the Lewin current, which has been pushed by the trade winds to come down here, a warm current, and the difference in rainfall because of that warm current. It's quite dramatic. Australia kept drifting to the northeast, and by about 24 million years ago, the southwest was truly isolated, deserts to the east and north, and oceans west and south. Now, a little event happened, it was happening from about 3.5 million years ago, but it really happened 2.58 million years ago. Can anyone see what it is? Whoop, there's that. The Panama Isthmus was formed, and that had again a dramatic effect, because instead of this happened as the Americas drifted further to the west, and whereas there had been an equatorial current flowing from the Atlantic into the Pacific, that changed to being what's called the Atlantic Meridional Overturning Current, part of which is the Gulf Stream. And that brought a lot of warm water up into the Arctic. Warm water evaporates quickly, and through condensation it then precipitated, and you get the formation of sea ice. That took up a lot of water, and eventually continental ice over adjacent areas, and that was the beginning of the ice ages, just because of this small change there. And the ice ages resulted in, during glacial periods, I'll come on to this. The Milanovic cycles, the Earth goes around the sun, and the angle of tilt changes, and the direction of tilt changes, and the distance from the sun changes. And these are mainly because of different gravitational pulls from the planets at various times. So you get a situation where this affects the temperatures mainly in the Arctic areas and mainly in the Arctic as against the Antarctic. The Arctic is sea ice. It's got some continental ice like in Greenland, but the Antarctic is basically continental ice. It's very stable. And when you've got the situation of the Earth being furthest from the sun, the tilt being in one direction, you'll get a lot of ice formed in Antarctica, in the Arctic. It won't change very much in Antarctica, and the reverse will happen when the planet is close to the sun and conditions are right. So you get a change from ice age to interglacial, from glacial periods to interglacial. And this does relate to Western Australia because during glacial periods, sea levels were about 125 metres lower than they are today. And the most recent one was only 18,000 years ago. And 18,000 years ago, you know, this is when Homo sapiens were well and truly established in Australia. The coastline was out here. And it has since been back as, well, not since 18,000 years ago, but at times it has been back that far. Populations, of course, were much like today in that they hug the coast. The coast is where sustaining life is a lot easier. So you can imagine the effect of them having to move back into other people's land consistently. And there's quite a few stories that, and particularly from Queensland, where fathers have told sons that we used to gather food at this place and now the ocean's come up. It's turned into a science called geomythology, where they look at some of these myths and establish that geologically they are fact. And the myths might be related to tsunamis, volcanic activity, a whole range of things. And this is when, with the ocean floor exposed, most of the floor was made up of remains of shells, corals, all calcium carbonate, and blown ashore to form sandhills, which then formed what's called the Tamala limestone, which is where the caves are, and it is along the western side of the Loon Naturalist Ridge. And this is just behind Narrabeen, where you've got these young sediments of wind-blown lime. And this is the extent of the Tamala limestone, almost to Albany.
Excuse me, is it all wind-blown limestone here, or is there any ocean sediment?
Yeah, look, there's very few real ocean sediments. There's some down south, but it appears sort of almost 95%, I'd say, is windblown. Yeah. So with the low sea levels, this enabled migration to Australia. They still had to do some navigation, but there's certainly a lot of easier travel. And interesting, about 14,000 years ago, sea levels were rising at the rate of 4 metres a century, and perhaps in any one decade a lot faster than that. And there has been sort of broad dismissal of sea levels being able to rise at 50 centimetres a century or even less. You know, people say, oh, come on, that's just ridiculous. Well, it happens, and it can happen again. Yeah, Rottnest Island, up until 6,000 years ago, was part of Western Australia, part of the landmass. And I thought I'd show these just to, you can just see how vulnerable some of these areas are to even a small sea level rise. And of course, with global warming, you don't just get sea level rise, you get more storms, storm surges, more rain, possibly. And this is down in Augusta. These sandhills, which protect a lot of this area in eastern Augusta, you can see they're pretty much ephemeral. It wouldn't take much at all to change them. Just a quick one on water and soils. Very different soil types in these areas. If we look at a cross section, we have these coal measures, and during the Permian, when I say coal measures, they're basically sandstone formations with relatively thin seams of coal. And above that we have the Agadir Formation, some volcanic activity as India moved away, and the Leaderville Formation. So these are the main aquifers. There's rainstone, you get evaporation, you get transpiration from plants, flow into rivers, and almost what's left over recharges the aquifers. So a 10% decline in rainfall might result in a 30-40% decline in aquifer recharge. And it's something that I'm sort of passionate about, because at time of drought, a lot of, the attitude is, don't worry, we've got the aquifer, we can just take it from there. And it's just not that simple. These formations are up to 140 million years old, and the oldest water in there is about 40,000 years. Most of the water is a lot younger, because it goes through them and runs out to the, if it doesn't run off from the streams or evaporated, it will go into the Indian Ocean or the Southern Ocean. And these are the what are called groundwater dependent ecosystems, and most of them are the streams that are in the trough, but also the coastal plains. The coastal plains have a lot of iron oxides, a lot of iron sulfates, and when they are exposed to the atmosphere, to oxygen, they will oxidize and form sulfates and sulfuric acid. The Beanup mine, the BHP mine down in East Augusta, they dug up the material and exposed it to the atmosphere, and that oxygenated it and or oxidized it rather, oxidized the iron, and so they have still sulfuric acid in the water there, and they have to neutralize it with limestone, which they dig up from the ridge, and it's a complete, Oh, look, I just showed that because Margaret River is the only river that flows through the Leuin complex, flows through the Leuin Naturalist Ridge. Any other stream that flows into the ocean here originates on the ridge and flows down it. And again, it's a nice little sort of, a geological mystery as to why it went through there, because everything is a line in this direction, and yet the Blackwood River hits the ridge and turns to the south. The Margaret River flows along the ridge, parallel to the ridge, and Margaret River goes straight through it. I don't know why. So this is the aquifer. This is where we are. And this is the limestone on the western side of the ridge, which is a karst limestone. That means it's got lots of holes in it, caves, cavities, and you can get water from that, but it is ephemeral. If it rains one year, most of the wells will produce, and they don't last for long. So very different soil types. On the ridge, most of the soils are like this. There'll be, as the granite or granitic gneiss weathers, most of the minerals will be weathered to clay, but the quartz will remain as grains of quartz. So a typical profile is sand at the top, and then clay, and then onto granitic gneiss, which is very good because the sand is well drained and the clay is water retentive, so this is mostly in the range of 1 metre or a couple of metres thick. Very nice for vines, they like that, and many plants do too. They like it well drained, but they can survive during summer. So over to the east in the trough, it's sort of sand, but sand on sandstone, and of course limestone on the western side of the ridge. And very different pHs, of course. Yeah, it can vary a lot on the ridge, and this is just on our place where this is the sand going into clay at the bottom, and the same here, but just a very different, the sand looks quite different, and again onto clay.
Same property?
Same place, yeah, just down one of the,
How far
yeah,
apart
both.
are those?
Probably it would have been 120 metres, something like that. And when we planted trees along Carter's Road, every hole was different. You know, we hand planted. And Bunbury Trough, basically sand. So all the gold medal wines come from on the ridge. Laterite. Laterite's formed during winter. It rains and dissolves some minerals, carries them into the water table, and during summer, capillary action will draw some up, and they'll basically crystallise or form a layer around a little grain of something, and year after year that layer will be built up, a bit more will be added on. And the important thing about laterite is not the laterite itself, but all the holes in it. It's a very good aquifer. It's called a superficial aquifer because it's very shallow. Bauxite is laterite with a lot of aluminium in. So when they mine bauxite, they remove this aquifer, and it really hit home when I was in Karajini. And here is the laterite. I went up one year with the grandkids, and it was after a flood, And I said, oh, look, we won't be able to get down into the gorges. It'll be, the creeks will be too strong. Of course, they were fine. And a few years later, I went up after there'd been a real drought up there, and I said, we won't, the gorges won't be any good. There won't be any water in the creeks, and the creeks are just fine. And the reason is that this laterite forms a huge sponge over that plateau, and the water slowly drains out of it. So you can imagine what happens when they mine laterite. Instead of that happening and feeding the coastal creeks, the creeks that run off those regions, it'll come down in a rush and then dry out in the summer. So, yeah, apart from all the other aspects of laterite.
So basically the laterite is like a literal sponge when it's raining and it gets saturated.
Yeah,
And then
exactly.
through the dry period it's slowly releasing that
Yep.
the interface. Okay.
Yep. And it's up to about 15 metres thick. It's pretty substantial. So this area was isolated, and you can see, wonderful range of vegetation. The vegetation is rich because it's been exposed for 250 million years, and it's been allowed to evolve, but it's also been weathered a lot. The minerals have been carried away. They don't call us sand gropers for nothing, because there's a lot of sand, nutrient poor soils, and plants, and following that insects and then birds and mammals have had to survive in niche situations where they can survive. So it results in a lot of diversity, as can be seen. This is down in Geologist River National Park. Just fantastic. And what struck me is that if you go through the park, the vegetation changes dramatically from area to area, despite the fact that there's strong winds blowing seeds around, blowing dirt around, but it doesn't, you go from one group of a little ecosystem to another one.
Is that because of the soil change?
Yeah. So this is the southwest floristic region. About 8,500 plant species. And of course the plant species that are formed on the sandhills and, the very recent formations have been derived from the adjacent cratonic areas, so they are reflective of that long exposed area. But I thought this was interesting, that these are areas that have also been exposed or are also very old rocks, comparable to those in Western Australia, but they haven't been exposed. This one was glaciated seriously up until 18,000 years ago, and really just cleared 11,000 years ago, the last of the Ice Age. And it's only got 120 plant species, even though it's adjacent to a relatively rich area, and the plant species have migrated into it, but slowly. And look at the Amazon, quite amazing. It's never been glaciated, and it makes southwest of WA look pretty timid in comparison. So yeah, what we've done, I'm just going to get through to this right. This is the extent of clearing for the wheat belt, and I don't want to dare suggest it's cause and effect, but you know, the rate of clearing and the decline in rainfall, was just so well aligned. I remember the first time I came to Western Australia and flew back. It was end of summer, and flew back over that sparse, brown or yellow landscape, and thought, well, crikey, you know, how there's nothing happening. It will never, And there have been papers written to show that, explaining the reason why clearing of forests actually result in reduced rainfall. Look, it's so complex that I'm not suggesting it's just that, not by any means. But I'll go through this. This is, I hope there's no meteorologist here, are there? Because this is, look, you'll have to bear with me, because this isn't working very well, and I'm not working very well. So this is the calendar year rainfalls, and I like to look at them also, looking at...
Sorry, Peter, is that the rainfall for this area?
Yes, this is in our gauge on the farm here, and you can see there's pretty low rainfall here, but looking at annual rainfalls, but not starting from a calendar year, looking at rainfalls over the summer year, July one year to June the next year, the picture is even more dramatic. That this was that summer there, and it's illustrated here. This is the average during that time, and that was that summer. Well, that whole 12 months, every single month was way below average.
That's what your total was, 556 mil here. In that year.
Yeah, and that's the average. This last period, this last year measuring that time was 1,050. Now, why did that happen? And this is where I was hoping there was not a meteorologist in the room. 2019, 2020, there were the bushfires in Eastern Australia, and they were really dramatic, and a lot of material went into the stratosphere to a height of about 29 kilometres. In 2022, there's the Hunga Tonga volcanic explosion, and a lot of that material went as high as 58 kilometres into the atmosphere. Now, the atmosphere around the equator is a lot warmer and a lot wider, a lot higher. Where it's cold around the Arctic areas, it's colder and more condensed, and it's not as wide. So because of that, you get a drift of the atmosphere towards the poles. And this shows the effect of the Hunga Tonga explosion 6 months after the explosion, where all the water vapour and all the particulates from that explosion had gone up into the stratosphere, and the stratosphere had drifted down towards the pole, and the temperature difference measured in the stratosphere was dramatically colder in that band. So as this material from the Hunga Tonga explosion and from the bushfires drifted south, as the atmosphere drifts towards the poles, the rate of movement affects the polar vortexes. If it's moving very quickly, the vortexes will be controlled, they'll be disciplined. If it's moving slowly, the vortexes begin to wobble. And we've seen this a lot in the northern hemisphere. Because the Arctic is warming, it's got sea ice, and because it's warming a lot faster, like 3, even 4 times faster than the rest of the globe, the temperature difference between the temperate zones and the equatorial zones and the poles is a lot less, and the movement is a lot less, and the vortex, and therefore the underlying jet stream in the northern hemisphere is wobbling. And you'll see it in particularly in America, where often there's drought and very hot conditions on the western side of the continent. Over on the east, and even down into Louisiana, it'll be very cold. And that's because that vortex is doing this. So this is when it's strong, this is when it's weak, and you get this wobbling vortex. And I've never seen on Google search what happens in the South Pole. They always look at the northern hemisphere. But as these particulates drifted south, hang on. Yeah, the oceans are getting warmer. And there's a lot of sea ice melt in the Antarctica. This is Antarctic sea ice, and this is the average here. So during that period, that drought period, 2023-24, sea ice was low, but gravity measurements showed that there was an accumulation of ice in Antarctica during that same period, which seems pretty odd. Particulates and the sulfates, particularly from the Hunga Tonga explosion and also from the bushfires, drifted over the South Pole. It's easier to do it without these diagrams. Drifted over the South Pole, and they partially destroyed the ozone layer. The ozone is a very effective greenhouse gas, and it cooled a lot over the South Pole. And there was an accumulation of continental ice, even though there was warm water drifting down to melt the sea ice. But also that warm water caused a lot more evaporation, and combined with the colder atmosphere, there was more precipitation. So that added to the amount of continental ice. So it was very cold over the Antarctic at that time, and that resulted in a very controlled vortex around Antarctica. It's called the southern annular mode. Now, when the vortex is wavering, it enables these low systems to drift up higher. And when it's not, it keeps them down low. And it changes the flow of the systems across the southern part of Australia. So in normal times, well, normal, when it's, there's a lot of average times that are neither like this or like that, but just average. And I'll call them normal times. You'll get lows coming up and delivering rain, and enough system moving across here that it keeps low systems from the Tasman Sea and the Coral Sea pushed out from eastern Australia. But when it's like this, a tight vortex due to a cold Antarctic, the lows won't reach up here, and these low systems from the Tasman Sea are able to drift into eastern Australia and cause a lot of rain. And that's exactly what we had. While we were in drought, they were getting flooded over east. And most of those floods didn't go further west than the Great Dividing Range. They were all coming in from the Tasman Sea. So look, that's mucking around on the computer and, you know, looking at this and looking at that and trying to put it together. I'm not claiming that's right because, as you mentioned, the meteorology, the systems are very complicated. They really are.